All right. So for the warm-up, look at your notes. Write the flow around a circular cylinder is one of the three superpositions of basic flow. Anyone read the book? Anyone know what the other two were? We did one of them last time. Yeah?
Ranking oval.
You ranking oval? What was the one we did last time? What was that called? Sorry?
Half body?
Yeah, half body. Well, half body, circular cylinder, and ranking oval. Those are basically the three that the book goes over. They're good practice to go for the quiz. So in the quiz, I will give you the velocity potentials and the stream functions. For bonus, you should be able to derive them, I would say. So here, the flow around a circular cylinder, far away we have a uniform flow. So it's going to be a combination of a doublet plus uniform flow. In general, I'll give you the best coordinate system to use on the quiz. You shouldn't have to transfer it back to polar. Or if I give it to you, and if I give it to you Cartesian, you should stick with Cartesian. If I give it to you polar, you should stick with polar. Here I'm suggesting you should use polar. So maybe from your notes, see if you can look at, so just to review, right? So we got these two functions. Potential, which kind of looks like equipotential lines around here, and stream functions, which is a lot more physical. These correspond to lines where the fluid is tangent to, right? So I just drew a streamline here. This would be an example of like a baseball. So I'm going to use U naught, just because my U's are sloppy enough that capital U and lowercase u are not super clear. So I'll use U naught. So this is a given. It's the uniform flow far away. If people want to model, for example, the drag on a baseball, they don't actually throw a baseball through a wind tunnel. They just keep the baseball stationary, like so, and then have the flow go past it. So there's one potential stream function, one potential streamline. So go from your notes and write what a doublet plus a uniform flow is. And you have to use, theta, r. So you have to use stuff like this, r sine theta, x equals r cosine theta. So see if you can do that at your seats. Once you've done that, take the derivatives I've written up the board to figure out the radial velocity and the theta velocity. This is basically like horizontal lines. Just like the equation of a horizontal line. That one's right. Yeah, I guess we could write it like that too. You should use K though. We're going to use an A later. Okay, we're getting far enough. I think I can start writing on the board here. So the other thing on the quiz, I won't be giving you a picture. You'll have to deal with kind of like your intuitions here. So in general, I would start with the stream functions, just because they're easier to visualize. And we know uniform flow stream functions correspond to what kind of lines? Yeah, horizontal lines, right? So horizontal lines, that means every single y coordinate has a separate stream function. Y equals 0 has one, y equals 10, y equals 20, y equals negative 10, etc. So the first one is going to be u times y. But we're going to be in polar, so I'm going to use u times r sine theta. U naught. So that should be very clear to you. How to write the stream function for horizontal lines, for uniform flow going to the right. If we have to the left, it'll just be a negative sign. That's all. All right. And the next one is just I forwarded you the quiz from last year. The first page is identical to what I'll give this time. Here we have the doublet, which is we talked about is basically when you take a source and a sink and you put them closer and closer together and you put them right on top of each other. And that will just be copying off the front of the page. Now, one key thing to notice here is that, so superposition. So we basically have these two functions, and we're trying to figure out what the flow looks like with the two of these interacting together. Every time I introduce a new flow, I'm introducing a new constant. For example, this one I've got u naught, which is the speed, and this one is the strength of the doublet. Okay. Now these two are going to interact, and if you remember what we did last time, when we have two constants, we can take one of them and replace it with a different constant. That's more sort of suitable to solve the problem. For example, just to review last time, we had an even simpler problem, the half body. So it looked like this. I should go draw the axes first. Okay, so the half body, and some people did, I was pleased that some people did try to work out the details of how we did this last time, and that's important because you will need to have the details on the quiz. So half body is the sum of a source plus uniform stream. And the psi we wrote last time was u naught r sine theta, just like we have this time, plus m over 2 pi theta, which corresponds to basically radial streamlines coming out. So we basically got stuff coming to the right, and then we basically have like a kitchen faucet adding stuff in all directions. Each of those corresponding to a different stream function theta. So again, we had two constants, a u naught for the strength and u naught for the speed and an m for the strength. And there's going to be a point on the x-axis where both of these streamlines are facing the same direction, and they're going to cancel. And that's basically going to give you what do we call that? Yeah, this is the stagnation point. Okay. And we labeled that a point B. So basically, given these two, the way these two looked, we were able to derive a new point B, where basically your speed was 0. And afterward, we basically we rewrote what psi was using. So psi was originally in terms of u naught and m. We rewrote it in terms of u naught and b. Okay. We replaced the strength with this physical distance b.
What's that term in the numerator? It's like something over 2 pi.
M.
Oh,
M.
lowercase m.
Like M&Ms. I saw some M&M people dressed up for trick-or-treat. Yeah, M. It's for strength. So you can be basically, it'll make the problem easier, you can replace this strength with this units of like flow rate per unit length on the board with this physical distance B. So this is a distance, and this is a strength. And that's basically the technique they do. As long as you got two constants to vary the flow, you're fine. If you remember last time, we showed that M was over M over 2 pi U naught. It had to satisfy these characteristics for that to be the stagnation point. Okay, so you can use B and M interchangeably. So convert problem to using B instead of M. And they're proportional, so it's basically just a matter of nomenclature. Okay, so that's what we did last time. Now, this time we're going to do something very similar. Does anyone have questions on how exactly we did that? Do I need to work that? Should I work that out? And we have time if people want to see how we did that again. Does anyone? I think I heard voice of God say sure. All right. All right. So to get this, so first we write UR. So UR, let's go up here. So UR, in this from last time was 1 over R d psi d theta. And that was U naught cosine theta plus M over 2 pi R. Okay. And we certainly need that to be 0 for a stagnation point to happen. And physically, this is also really important that you understand the picture involved. If we have this source coming from the left, and we have a stagnation point there, the stagnation point has to be at theta is equal to pi. And this is theta equals 0. Okay. Why isn't there a stagnation point to the right at theta equals 0 on this side? Yeah? Yeah, that's exactly right. So basically, like, the stagnation points are about the flows basically going in opposite directions. And here, the source is going to that direction, and this one is going to that direction. In fact, as we showed later in the problem, the body that we're modeling is basically doesn't even end on that right-hand side. So this is the only conceivable point you can have U and B equals 0. So we got theta, if theta is equal to 0, so basically just from the picture, theta is equal to 0. And if theta is equal to 0, UR is equal to U naught plus M over 2 pi R. And for this to be 0, you need to have there's something wrong.
Is theta equal to pi at the stagnation point?
Hold on. Theta is equal to, theta is equal to pi. Yeah, there we go. Thanks. So theta equal to pi, so this will give you negative U naught. And then for this to equal to 0, we have M, well, let's just rearrange. The big important thing is R is equal to U naught upon M, 2 pi U naught over M. Okay. So that's how you figure out the location of the first stagnation point. You kind of use the picture to figure out what theta should be. Once you have theta, you figure out what R should be. And R, in this case, we call this B. Because it's given by, if U naught and M are given, you know what B is. And so that's how we got this. And you can show similarly that U theta is going to be 0 on that point as well. Okay, so what we did then, once we figured out the value of the stagnation point, the next steps were we figure out psi at R is equal to pi comma B. psi at theta comma r equals psi pi comma b, and then we just substitute that to the original expression, and we got pi b u naught by substitution, and then we basically said pi b u naught is equal to this thing, and that gave us the equation for the curve. So that's what we did last time. But the only thing I wanted to highlight is that basically you go from u and m to basically this new variable b. Okay, so is that good? Okay. All right, so now to this problem. Now we're starting with r and k. Let's get rid of this stuff. We're going to do it later. R and k, u naught and k. And you can also rewrite this like so. U naught minus k over r squared, r sine theta. It's useful to write it like this because then you can separate theta and r. They're kind of like independent. To get stagnation points, you have to have u and v to be 0, but this is one way you can write it. Okay. And when you write it like this, you see something interesting. That if you remember from the half body, we call lines of constant, basically lines of constant psi correspond to lines that the streamlines can't cross. You just write this. So they're special. And that's how we basically model physical bodies. Because, for example, you can basically immediately see, based on this way we've rewritten here, that there's one line at psi is equal to 0. And that corresponds to constant r, right? Psi equals 0 corresponds to this parentheses expression being 0. All right, so psi equals 0 if u naught minus k equals a, if u naught minus k over a squared is equal to 0, that means k equals u naught a squared. All right. So psi is 0 basically corresponds to the circle I've drawn here. Which again won't be given to you on the quiz. You won't have any pictures on the quiz, but and we can rewrite this A using the original strength kappa. Okay. So that means any streamlines that basically start from the left, none of them can penetrate that circle. That circle is basically like an impenetrable barrier. Sure, you can there's actually going to be flows inside that, like you could evaluate any point inside the circle, but for the purposes of modeling flow around baseballs, you don't want to do that. Does this sentence make sense to everyone? Do people understand why you can't have streamlines cross that circle? It's because of the physical idea that streamlines can't cross. So let's say let's just draw like this little scenario here. The reason why streamlines make sense is because every single point in the flow field, like I'm going to just draw arbitrary points, have to have only a single streamline that go through it. So every point in flow only intersects a single streamline. Every point in the flow only intersects a single streamline. That is the case for steady-state planar flows. So let's say I did have let's just get a different color. Let's say I had a hypothetical situation where a streamline crossed. Okay. So let's say this little mole here that basically had a streamline that basically went like that. Let's make it a little bit crazier. So, well, physically, what that means is that, that means if I had to, like, smoke here, it could land here. Or if I had smoke here, it could land here. But then the problem is that particle doesn't know where to go. It could either go to the green or the blue. And for any flows that are steady state and satisfying these conditions, you cannot have, like, the particles can't have choice. They've got to just go along their merry paths. They can't have anything like this. Stuff like this is only the case for turbulent flow, unsteady flow, stuff that is basically cannot be solved with these methods. So once I've basically picked a point, there's a stream function that goes through it. Okay. Hopefully this gives you a little bit intuition for why this is. Okay. So does that make sense? Okay. All right. So you can't have any. So once I basically have this line of psi is equal to 0, being this circle, nothing can penetrate it. I might as well like make it like a rigid. All right, so now that we've defined kappa that way, the other thing is usually useful to use, kappa is not a very useful term because it's very difficult to draw. So that's why most people who continue with this course do not differentiate with kappa in there. They substitute with kappa is equal to u naught a squared. So that's what we're going to do. We're going to make that substitution. And this, so these methods, historically, they go back a very, very long way. I'll talk a little, but they basically quiz 6 and quiz 7 proceed by like at least 100 years. All right, so we do the substitution, then we have psi is equal to u naught r times 1 minus a squared over r squared times sine theta, and phi u naught r 1 plus a squared over r squared over cosine theta. And I would say generally you're going to have psi and phi to be actually quite similar, and that's because one of them, they're basically perpendicular to each other. All right. All right, so see if you can, at your seats, now take the derivative to figure out u r and u theta. And you definitely should be able to do this now. It's good practice for tomorrow. All right, so everyone do u r and u theta. All right, so you should get u naught 1 minus a squared over r squared cosine theta. And this one you should get L1 over R theta. U naught 1 plus A squared over R squared. Okay. Okay, so if you want to draw this, you've got this thing here. Does anyone need to go over how to do this? No, how to get UR and U theta.
Why is there nothing coming out of the A squared over R squared terms when we're doing d phi dr?
Here, let's write d phi dr, or you could also write 1 over r d psi d theta. Well, if you do 1 over r d psi d theta, it basically, you divide by r and then you basically take that with respect to theta. That's probably the easy way to do it. If you do the other way, you're basically going to use a chain rule and you're gonna get rid of stuff. You have basically that plus that, and it's going to turn into this. So it's probably easier to, well, that one's easier to use R, U, and this one's easier to use theta. Do you need to work it? Do you want me to work it out, or you're good?
No, it's okay. Thank you.
Okay. Okay, so remember, this is the radial velocity, and this is the azimuthal. All right, and theta equals 0 is here. Theta is equal to pi over 2 over here. In particular, for theta is equal to pi over 2, the flows are perfectly to the right. So there's no R component. So for example, some people call that like a flow profile. So this dotted line, let's say I want to show the speeds along that location. At theta equals pi over 2, it just basically, the speeds just go up with velocity, with distance, okay? Sorry, they go down with distance. So basically really far away, they're small. They sort of get up higher. And so the flow kind of looks like this. Okay. So out here, you can have basically U naught, speeds of U naught, and then they're basically going to hit this thing. And at the surface of the cylinder, so this is the part that's sort of not physical about potential flows. In a real ball, in the next quiz, we'll talk about something called no-slip condition, which is that basically when fluid basically slides past the boundary, the molecules that are sliding right past the boundary have to meet the speed of the boundary. And so that would be the speed of 0. But because potential flows don't have any viscosity, viscous forces are what's required. Because viscous forces are about shear, and that's what's required to slow down fluid. The surface of the cylinder, you get a constant slip. So at R equals A, you can substitute UR is equal to 0, and U theta is equal to -2 U naught sine theta. Okay, we can just get that by substituting in. So basically, you're going to get this constant slip around the cylinder. Can anyone tell me where the maximum velocity is? At least on the cylinder.
Of the cylinder?
Just on the cylinder.
would it be at 90 degree or pi over 2?
Yeah, and there's one more.
Well, I guess, whatever, 3 pi over 2?
Yeah. So that corresponds to what place on the cylinder? Yeah, so basically, you got U max, it's going to be like this, some crazy thing, and U max. So maximum velocity at theta is equal to pi over 2, and theta is equal to negative pi over 2. So you should also be able to do that.
Doctor Who, I have a really quick question. When
Yeah.
solving for UR, is there a reason that you wanted to do d phi over dr rather than the 1 over r d psi over d theta?
You would get the same thing. These are equivalent. It shouldn't matter which one you do. One of them leads to a little bit more algebra. For example, this one you've got to actually do the chain rule. You've got to do derivative of that plus derivative of this thing times that. This one you just divide by r and do derivative of that. But these are going to give you the same thing. The information in the potential is the same information in the stream function. It's just rearranged a little bit.
How did you get? You said I see when you say at search cylinder r is equal to a, and so UR would be equal to 0.
Yeah.
Just because, I guess the surface can't be moving.
Well,
But
just because, so where does this UR come from 0? It comes from the fact of substitution if you substitute r equals a into this expression, this whole UR becomes 0.
okay,
So this is because
so that's
of substitution.
and we're doing the same thing at like u theta. We're plugging in r is equal to a at u theta.
That's exactly right. If you put r equals a, you get 1 plus 1. That gives you the 2.
Okay. All right. Yeah.
All right, here's an advanced question. Why did I draw these arrows to the right if this thing says u theta is negative 2 u naught sine theta? Yeah?
Is the way that cylindrical coordinates work is that counterclockwise is...
Yeah, that's exactly right. So u theta, so if I were to draw this thing, r, theta is this way. That should be perpendicular. But theta is, counterclockwise, u theta. So that's what we call u theta positive, to go in the direction of increasing theta. And we have flow going to the right, so that turns out we have this. And the reason we have flow going to the right is because that initial u naught on the very left-hand side was a positive sign. I mean, I could be really cruel and just change everything to negative and make sure that you do stuff with negative. But in general, people have stuff going from left to right because that's arbitrary. You can always just decide. So we've decided to go left to right.
But what about the max velocity at 3 pi over 2? Because wouldn't that be rotating counterclockwise in the positive theta direction? If what you're saying.
Sign looks like this. And so you got a negative sign from the fact that it's 3 pi over 2.
I thought you said it was because it was moving opposite to...
You have to include this sign notation in both these, when drawing both of these arrows. The first one you have just this because of u theta, and the second one you have both of them together.
Oh, so at pi over 2, since that's positive, the positive and the negative make it rotate clockwise.
Basically, if you substitute this in, you're going to get a maximum u at either of those locations. By maximum, I mean maximum magnitude.
Yeah.
Maximum magnitude. Indeed, like this one, you might change sign. Okay, and we should have them going through both these directions because also you should use the fact when you draw these things, there should be a line of symmetry. Like basically, this y equals 0, everything on the top should be going to the right, everything on the bottom should be going to the left. All right, so you got max velocity, and the max velocity is a magnitude 2u. So that's the 2u naught. All right. So this was actually done. So this model, this was done by D'Alembert. or anyone French? How do you say that in French? D'Alembert? D'Alembert. He did this. This is back in, like, I think 1800s. They were trying to understand the drag on objects, and all they had was Newton's laws. So D'Alembert and a few others proposed this potential flow that would basically solve for conservation of mass and give you realistically looking streamlines. Like, they were really happy. You know, they drew all this stuff. I don't think they were using quill pens, but I don't think they had ballpoint either. But they were using like fountain pens to write all this stuff. They didn't have any calculators, and they saw these really cool streamlines. They're like, hey, that kind of looks like flow around a baseball. But then they were really disappointed because they actually calculated drag on this thing. And it turns out if you integrate the pressure along here, you get 0. And if you integrate the lift on here, you get 0, which means that this object shouldn't have drag or lift, which is incorrect. Ultimately, the big problem issue is the slip condition. So basically the fact that basically you have this fluid slipping along here. In reality, so I'll draw in green what the reality is, and that's something we're not going to model. In reality, we're going to have a wake. So in reality, if you have a baseball, depending on the Reynolds number, you're going to have a wake of various size. But basically, you're going to have something like here, where basically flow streamlines are certainly crossing, and they're doing weird stuff in the wake. And basically, you have a high pressure here and a low pressure here. This high pressure is going to push this thing back, and you're going to get drag. Does anyone know how golf balls work?
Like the dimples?
Yeah. How do they work?
I thought they were trying to make. Weren't they trying to? I can't remember if they were trying to convert from laminar flow to turbulent flow, or something.
It had to do
like
with the point of separation. So the golf balls. I think golf was invented in, was it Ireland? Oh, Scotland. Got close. Scotland. They basically used to play golf ball. They used to play golf on those greens in Scotland, and they used to use this. They didn't use wooden balls. They used basically balls made out of the sap of this tree. They would just mold into this ball. And over time, they found out that people got essentially better and better at golf because they could hit old balls farther than the new balls. Old balls basically had a bunch of pit marks from all of the places that you basically hit it. What the pit marks do is they basically they hold the line. They basically change the separation points of this wake and essentially make it smaller. With a smaller wake, you can basically change the pressure differences between here and here, and you get less drag. It can be optimized so much that if you basically have dimples of the right size, the ball can almost go like it has half the drag, and I think it basically, I don't think that goes twice the distance, but it can go like substantially farther. Nowadays, they do the dimples. Like every golf ball takes about $50,000 to do the CAD modeling, the modeling of the basically you got to make sure the center of mass of the golf ball is right there, even with all the dimples. And there's a huge amount of work. So it's about $50K to propose any new golf ball. But we're not going to talk about the wake. We're not going to talk about the dimples. We're only going to talk about why the pressure is 0. So it took them basically 100 years after D'Alembert until basically until they discovered viscosity. And then there's this guy named Prandtl. German guy, I think. Prandtl, he discovered that basically, even though these are high Reynolds number flows, so it's high Reynolds number, that means the viscosity is really low compared to inertia. At high Reynolds number, you can't just ignore viscosity, even if you get really good looking streamlines. It turns out really, really close to the ball, you have this basically length scale delta. And that's where viscosity comes into play. So if you look at like real streamlines of stuff going on, basically the velocity is u naught, everywhere is u naught, kind of like this says. But basically right within like what's called the boundary layer of the ball, which for a soccer ball I think is like 2 or 3 millimeters. The faster it is, it gets smaller and smaller. Within this boundary layer, the velocity goes from the basically far speed to 0, and it happens really, really quickly. And that's ultimately where you get a lot of the drag. But that wasn't discovered until literally like 100 years later. It was like a really long time. And we're not going to do boundary layers in this class. If you want to take graduate fluid mechanics. All right, so why is the pressure 0? All right. All right, so how to calculate the pressure on the cylinder? And you will have to do this on the quiz. You will definitely have to use Bernoulli's equation to calculate the pressure anywhere in the flow. And the key is you got to start with a position far away. So this is lossless flow. We do not use the loss equation for the energy equation here because there's no viscosity. No heating up, nothing lost. So the pressure on the cylinder, you start from far away, where you know the pressure is a P naught and has a velocity U naught. So this is far from the cylinder. And there you write the pressure at some point, ES plus 1/2 rho U theta squared. All right. So this is the pressure on the cylinder. We have P. Let's say we want to figure out the flow profile just on the cylinder. So we only care about the pressure on the cylinder in this case because we want to talk about the drag. In general, you can also calculate the pressure at any point. So we got 2 points on the surface, PS and U theta. Because we already showed UR is equal to 0 on cylinder. And if you're not convinced, you can substitute R equals A and see that. So that means U on cylinder is equal to, in general, is equal to U squared plus UR squared, and then is US equal to U theta.
Are those, on the left-hand side, is that U naught, or is that still U theta?
This is supposed to be U naught far from the cylinder. This one's U theta.
Okay.
So this is just algebra. I have to give you I think 1 or 2 extra pages because there's going to be a decent amount of writing on the quiz. As you can see, once you have 2 or 3 terms with the potentials, once you differentiate that, you get 4 terms, and it's just a little bit messy. So that's the pressure profile on the cylinder. You basically add up theta, and you get this. So to calculate the drag and lift, so velocity is going this way. So I'm going to box this. F. N is an outward normal. So to figure out the total forces, this includes the drag and the lift. That includes the drag and the lift. You can show that the drag term, if you integrate across the whole surface, so dA is going to go into, it's going to look like that.
Dr. Who, in the equation of PS is equal to P naught plus, is that a U theta squared or a U naught squared?
U naught squared. U. All right. So when you look at drag around a cylinder, theta being in radial coordinates, A times d theta, the radius times d theta gives you dA. And this is called drag, and this is called lift. And because of this, you necessarily have to have this cosine theta term if you want to consider the x direction. And if you integrate this with respect to cosine theta, you can show with a decent amount of algebra, I think I had that in the quiz one year, that this is 0. And same, the lift is also 0. All right. And ultimately, it's because the pressure is symmetric. You basically can only get drag if you've got basically an asymmetry in pressure being higher in the front and lower in the back. But if you plot this, theta equals 0, because it's sine squared theta, it's agnostic to theta equals 0 or theta equal pi. So that's not good. So this is called D'Alembert's paradox. Paradox meaning they know it can't be true because real cylinders have drag, but they have no other way to get around it. All right. Yeah?
Two quick questions. So did we assume that E naught would equal to 0 in that case? Oh no, sorry. Okay. You would add it. Sorry. So my second question would be to solve for U naught.
Yeah.
Would you rearrange the equation for U theta?
Oh, you mean how did I get this? How did I get this from here?
Yeah.
I just subtracted. I just moved all that stuff to this side, and I substituted in the expression for U theta.
Okay.
So I just substituted that in up here, and I did some. All right. So remember this. This is given. This is given, and theta tells you because we're talking about a cylinder. Oh, that's terrible. We're talking about as a cylinder, all we want is a pressure profile as a function of position around the cylinder. So I'm just having it as a function. Okay. So D'Alembert showed this, and that's all we're going to get into.
In the second integral, is that P sub r sine theta?
P sub s.
So P sub s in both cases? Oh, just
yeah, P sub s. So it's basically you substitute this pressure profile, and to basically get the x hat component, you basically multiply everything by cosine theta, right? And then to get the y hat component, you multiply everything by sine.
Okay.
Cosine theta gives you the component. So, for example, you're going to get an arbitrary pressure force, I don't know, let's say in this direction. The component, if you basically want to integrate figure out all the x forces, you basically take all of these and consider the horizontal component. This is basically the horizontal component of the pressure force. And this will be the vertical component. All right. We don't have too much time. All right. We have to do, I want to do the Magnus Effect, and then we'll have just a brief amount of time to talk about ranking ovals. I do have a formulation that's a little bit more clear than the book. The book does radial coordinates. I think that is not the clearest. So what I'm going to tell you is not going to be the book. All right. I think someone might have proposed a course project on this. The issue is the effect is generally pretty small. If you remember the very first day, one of the first weeks of class, we took that styrofoam cup and I spun it. And it didn't fall straight down, it just fell to the right. So this is basically what's responsible to curve balls. And it's basically uniform flow plus a doublet plus a vortex. And using the same knowledge that we learned last time, so the thing is, once you add stuff to the potential flows, you can sort of keep what you learned from the previous steps. So from just a cylinder flow of the cylinder, we knew that we don't have to use the strength of the cylinder. We can use the size of the cylinder instead to parameterize this. We're just going to add this new term. All right, and of course, this corresponds to the vortex. All right. And again, when people care about lift, they don't necessarily care about the flow profiles everywhere. They only care about the flow profiles at r equals a. And u theta, at r equals a, u theta is equal to negative d psi dr -2 u naught sine theta. So again, this is very similar to what we had before, except you have this new term.
What does the numerator in that new term represent?
Let's just let you do it on your own. Gamma is called the circulation. In the vortex, I think the notation we used, I think we might have called it the strength, but it's just a constant, and it tells you the sign of the vortex. I think that's all that we need to know. So actually, I do want you to do this on your own. So do this at your C's, because you need to know how to take derivatives, and also you need to substitute at r equals a. I will give a couple like calculus identities on the quiz.
Know which trig identities to memorize and which not to.
I don't think you'll need trig identities. I try not to have stuff that's like, if you're going to need something like a calculus identity, I'll give it to you. But I try not to have you have to memorize very much. I don't want to test memorization. All right. So, all right. So you should get, and of course, if you take the derivative of a log function, you get an inverse, right? You get plus gamma over 2 pi a. You need to know how to do this. You need to know how to go from here to here. You have to do that several times on the quiz. Go from this to this. So make sure you practice doing that. Now the issue, we were very easily able to draw a clear picture for the flow past the cylinder. But here, the problem is it depends on the strength gamma. So you get a variety of streamline patterns. Basically, you get a stagnation point, theta equals stagnation point, where u theta is equal to 0. And that's corresponding to sine theta stag equals gamma over 4 pi u naught a. So, I mean, you take inverse sine, you can basically figure out what the stagnation points are. But because sine's periodic, depending on what the magnitude of this is, you could get 0 stagnation points, 1 stagnation point, 2 stagnation points, etc. So here it's not super easy to draw, but in general, when you have no circulation, you're going to get exactly what we had before. The cylinder kind of looks like this. And the whole issue is that we had a stagnation point in the back, which isn't really physical. And again, we have that line of symmetry. This is the case we had before. And so that's when the cylinder is not spinning. All right, so when you have this thing spinning, you think physically what's going on, you got all that incoming flow, but it's combining with the fact that the spinning is causing another flow. So basically, those stagnation points get moved up, and it kind of looks like this. Okay. The key thing is this arrow here. It's basically traveling, has the circulation gamma. Gamma is the integral of the velocity over the radius, so that gives you this frequency here. This is for gamma over 4 pi u naught a is less than 1. For for this one particular circulation point, you have one stagnation point. It kind of looks like this. And for really, really high circulation, the stagnation point's not even on the cylinder. It kind of goes like this. So it's like that cylinder is wrapped up in some kind of protective flow field. All right.
Hey, Doctor Who, above your first image, what does it say? It's getting cut off by the camera.
Oh, let me just lower that a little bit. Oh, that's weird. I didn't know it only went that far. I just tried to draw that here.
Usually it's better.
Oh.
Yeah, it's usually good.
Gamma is equal to 0. That's the camera. Oh, well. Did someone move the camera? Because we're getting a lot of the low board. No, I'm not going to even mess with it. I'm just going to break it. All right. And again, if you want to calculate the pressure, so we basically do something very similar to last time. If you integrate, spinning cylinders have no drag again, but they do have a lift. This is the lift force. So did have one thing on circulation. All right. Where circulation is defined as integral u dot ds. So generally, the strength of the cylinder is related to the circulation like this. K is equal to gamma over 2 pi. But basically this says if you throw a baseball, you're going to get, so the force, so you throw it, or a softball. If you spin it, there's lots of sports, like soccer, there's a really famous goal, like they did this free kick in Brazil that went around people. The lift force, the force that brought the styrofoam cup to the side, is going to be proportional to the density of air times the velocity of the fluid. So the faster you throw it, or the faster you spin it, you're going to get like double effect. You throw it twice as fast and spin it twice as fast, you'll get 4 times the force. All right. Yeah?
In the first part in the equation where you have in the parentheses -2 3 time theta, is that a R or a gamma over 2 pi?
This one? This one?
No, at the end of that line.
A gamma plus gamma over 2 pi a.
Is that also the resultant force is equal to 0, and then the force in the y direction is approximately, or is that equal to?
The drag force is 0, but the lift force is non-zero.
What's
Fx
this?
means the force in the x direction.
Oh, that subscript's in x, f sub x equals 0?
Yeah. Sorry, my handwriting must not be very good today. Daylight savings time here. All right, the last flow we got to talk about is Mr. Oval. Whew. All right, so this, what I'm going to put here is not in the book, or the book version is not very good, so all right. And we'll just talk briefly about this, because I do want to have time to go to the homework. All right. So this oval, this Rankine oval looks a lot like the cylinder, except, the cylinder was the doublet, where we had the sink and source right on top. Here we actually have them separated. So there's uniform flow.
Can you start the board, please, Dr. Who?
Oh, yeah. Plus source, plus sink. All right. All right, so let's just draw what that looks like first. I encourage you, I would say for every problem on the quiz, unless a picture is given, you should definitely try to draw a picture. Pictures give you kind of like this sense for where points are. If you don't have the pictures, you won't have any way to double check your math is right, and you're just you're gonna make errors you're not gonna know. So we got flow coming to the right. We have a U naught here. And I said basically a source and a sink. And ultimately we want to have a shape that basically has stagnation points in the front and back. So the source is going to be here, and the sink's going to be here. So the source is going to be in the front. All right. So imagine it's like kind of like a river going past like a fountain and then a drain. So just based on what we've drawn here, physically, can anyone tell me where the two stagnation points should be?
One of them would be in front of the source, correct?
Okay, yeah, that's good. So I heard some people say there would one be in the middle, and that would be true without the uniform flow, because clearly, no, that wouldn't be true without the uniform flow this way. Yeah, so let's just draw it in green. So the one in the front is due to the fact that uniform flow, the river's coming down, and this fountain's pushing back, so at some point there's something there. And stuff flowing into the sink, and basically you got uniform flow going past. The thing about sources and sinks, the flow decreases as you go away, but the thing about uniform flow, they're just uniform. So there will definitely be points where a constant is going to equal to whatever decreasing speed you have there. All right. So the stream functions look like this. U naught r sine theta. Again, this being y, associated with points y. And basically, you're going to have two separate points associated with these two theta 1s and theta 2s. Now, let's just draw it in green. All right, so this will be theta 1, and this will be theta 2. Because when you write these things, you write them without consideration of the other ones. So theta 1 is basically just if you're at some point r comma theta out here, the direction of the streamline, basically, you're just going to be, the source is just going to be shooting at you and just be sucked into the sink. So
that second term, is that m over
yeah, that's the same sign.
2y or 2 pi? I can't.
M over 2 pi.
Okay.
M over 2 pi. Da, da, da. Okay. And similarly, so you should be able to reason that out based on the definition of each of these things. And this one is U naught r cosine theta minus m over 2 pi log r1 minus log r2. All right. Natural log. All right. Deviated seeds can, so this is basically psi in terms of r comma theta, phi in terms of r comma theta. Deviated seeds, can you write them in terms of x and y? Because ultimately, this problem is easier with x and y, but the book doesn't do it that way. So convert the thetas to x and y, the r's to theta, using, you'll need to use right triangle, the hypotenuse squared is equal to this leg squared plus leg squared, and you have to use tan. Okay, we finish in about 8 minutes. After class, what we're going to do is try to answer some questions on the homework, and then we're going to have a little review session of people's previous quizzes. So to label this, we'll call this a point x comma y. Right? So just to help you here, if you have this, basically, this is theta 1, and then this is y, and this distance is x plus a. So we'll call this a. All right. Got it. Okay. All right. You're gonna have to practice this. Some people got it. All right. So psi. I already wrote the first part. U naught y plus. We basically have each of these components here. M over 2 pi is not affected by this, but to figure out that angle, you basically need to figure out the lengths involved. And the lengths, for example, for this first one is y over x plus a minus m over 2 pi. Y over x minus a. Minus m over 2 pi. Y over x minus a. Did I get the sign wrong? Should be this minus sign? And this one should be u naught y plus m over 2 pi natural log of plus a squared y squared minus m over 2 pi.
Just for clarity on the blue gene side, the phi and xy, or psi and xy is u naught y plus m over 2 pi inverse tangent of y over x plus a, and it's minus m over 2 pi inverse tangent of y over x minus a.
Yeah.
Okay.
I'm really confused as to what quantity is A.
A is the distance between 0 and the source, and 0 in the sink. So A is kind of like, has to be given in the problem. So given, okay, so we have given U naught and A. You're supposed to write the velocity field for the rest of it.
Hey, Doctor Who, for psi, should that be u naught y minus m over 2 pi?
I was thinking so too. Inverse tan. Theta's tan. Yeah, maybe mine. That's why I thought minus and plus.
And then in the first term, that's y over x plus a, and then the second one, it's y over x minus
Yeah,
a, correct?
this one has to correspond to the source, because basically, well, I've drawn a point here. It's on basically a distance x plus a. Yeah?
Wait, if we have A and then, why is it just one A? Because we have, it goes all the way from A to, or negative A to 0.
Yeah.
And then we have an A, and then we have another, whatever your X is.
Yeah, yeah.
So why is it only Y over X plus 1A? Because we're starting with 0. X plus A.
Because x is defined between this and the point x. And that is, you have A. So x is defined between this x equals 0 and that point x. For the same reason on the other side you have x minus a, because basically you got to do theta 2.
So are we just disregarding the right A and calling it X?
No, this right a, that's where the other tan term comes in.
On the right side is X plus
Is
A.
the reason for the x plus a and x minus a, is it because we're saying, I guess, the source is almost like the origin in a way, or
We're trying to
0.
figure out what the so the stream functions basically correspond to stuff basically pointing right to the point here. So this theta 1, that's basically, if you had no other flows would be going from your point there to your whatever arbitrary point in the space is.
For your 5xy, would u naught r cosine theta, would that be u naught x instead of u naught y?
Yeah. Yeah, you're right. Thanks.
Also, where did the natural logs come up from?
Those are just from the
Oh.
definition of source and sink. Those are given in the. Those will be given.
So you basically just rewrote the thetas in R in
Yeah,
terms of
that's all this is.
Yeah.
Like basically rewriting each of these R1s, because in the end we want these things as a function of x and y.
Right.
Okay, sorry, that's time. I think this is right. If there's a minus or plus here, let me know, and I'll correct it. But I think now we have it right. Okay, so what are you supposed to do with this? You're supposed to calculate where u equals 0 and v equals 0, show that these two are stagnation points, and ultimately, if you do this right, it's going to look like this, where that is basically just one streamline and stuff's going to go like this. So the two things you can calculate are the length, the width of the stagnation points, L, and the height of this thing, L and H of oval. I would say do that for practice.
So what exactly should we be expecting to have to try to figure out for the quiz? There's a lot of content in this section, and it's kind of, to me, all over the place. So what should we be expecting?
Basically, I'll give you stream functions and potentials, and you have to be able to calculate everything else. What stagnation points look like, what the profile will look like, what the shapes look like, and any potential drags or lifts.
Okay, and that's for like these complex things like the oval and the cylinder, or the circular cylinder.
Or any one that I give you. I think last year I gave people a different one. The only thing I'm going to give on the front side of the page are the basic potentials and the basic stream functions. Everything else you're going to have to do.
You're just going to tell us, right, to add like a superposition of a couple of those things, right?
Yeah. I'll say add these together.
Just saying, like, basically add a couple of these potentials.
Yeah. But for example, you saw there's a lot of work. Once you even written those down, you have to basically substitute for the constants. For example, the width of the cylinder, the stagnation point of the half body. There's a lot of sort of substitutions that you have to go with.
Do you think either today or tomorrow could you like post what you're gonna provide us? Just like
I already did. I sent an email about it. It'll be the same page as last year.
Oh, okay.
I think it was sent on Friday.
Okay.
Yeah.
Thank you.
Expected to make any sketches or just use them to help us?
You should be able to sketch it. Within reason, I would say. Like, this is difficult to sketch that. Well, once basically you solve for the equation for the oval, you basically just sketch it as best you can. You should definitely be able to sketch it far away. You should just sort of sketch it here. The stuff that you're familiar with, you should be able to sketch. The stuff that you haven't seen before, maybe that'll be a bonus or something. But you should definitely be able to go from stream functions and potentials and figure out stagnation points. That's definitely going to be on there.
Hey,
Okay.
Dr. Who,
Yeah.
I want to clarify. I want to say I just heard you say this. But on the quiz, did you say we'll be given like the whole? So if we were doing the rink and oval, for example, that we'd be given that this is uniform flow plus a source plus a sink.
Yeah, you should be prepared to just go from this statement. I might be nice by giving these two, but you should know how to basically go from there to figure out everything else.
Okay, thank you.
Yeah, because that's what I did last year. You see, last year, I think I asked people to add those together. I would say just practice the ones that we did in class and the homework, and that should be plenty of practice for the next 40 hours. Okay, so the people that want to remain, we've got office hours now. Does anyone have questions on the homework?
Some of the calculus derivations that they show, their step 1 doesn't match their step 2. And there's one question where they use the completely wrong numbers for their end value.
I said 2 corrections.
Yeah.
Does that account for it, or is there more?
I have to check.
Okay.
I think it's fine now.
Oh, you think it's fine now? Okay. It should be corrected now. Oh yeah, let's do this first. Yeah. Oh yeah. I was in Pi Sigma. 10, 11 to 20. There you go. Yep.
So what is one is, you asked us to present early. What would you expect?
Same as basically we give you 3 minutes. You can show stuff here, or you can, like with a PowerPoint, or you can show stuff there.
So like what week are you expecting?
Oh, what week?
Yeah, like when's
Anytime before the final. So not a quiz day, but anytime before that. So we have one more quiz after this. So you could do it Monday, Wednesday, or Monday after that, and that'll be it.
Okay.
Yeah.
Should we just email you beforehand and say, can you do this day?
Yeah, sure.
For the video, because we've got a 3-minute video and then we've got the presentation in class. What is your general expectations of the video? Right?
Those are just so people, like you saw last year, so people can actually like see it afterward. I think for the one in class, you just describe what you did and describe, maybe try to get some class interaction, like ask them to guess something, show them one demo in real time, and then you can show some other things on the video if you don't want to show other experiments in real time. Yeah.
So many questions, really just trying to figure out what day.
Yeah, and I'll go easier on you if you do it earlier because you have less time than everyone else.
Okay, we'll do it in the next week or two. And then one personal question is that last Monday, so is that mainly just presentations?
Yeah. And I think there's some people going to do it on Blue Chains.
Okay.
But that's usually one of the more fun days of class because you actually get to see everyone's stuff. So if you can come in person, that'd be great.
Then I'm trying on.
Yeah.
Thank you.
Okay.
Hey, I sent you an email. I spoke to Doug.
Oh yeah.
Yeah.
All the quizzes need to be added a couple points. Who basically got that wrong?
I had like a 3 meeting.
Yeah. No, there are a couple other people brought up that. What do you think the best way to do that is? Because a lot of people didn't even attempt that, so that's not good. Yeah, I'm definitely going to give you 1 or 2 points, but the question is how am I going to do it for everybody else?
So basically, I couldn't receive any credit for this part, but
Oh, yeah.
the only part that coding handbook, and we went over the entire part B.
Yeah.
And I did everything correct, so my algebra was wrong because I
Okay.
did D1 over D2 instead of D squared over D.
Okay, sounds like you should get +2. I told the grader just increase people's grades for that point that you didn't get it. But did you see any changes in your quiz grade?
I saw +1, but Django, when I spoke to Django.
Oh, you saw +1?
Yeah, when I spoke to Django, got it +1 from 5.
Okay, let's do 2. We can just do it right now. No, actually, I didn't bring my iPad today, so we just have to stay here. Okay. Hey, what's your name again? Pradeep. Yeah, you want to just come up? We'll talk about the homeworks and the quizzes together. Oh yeah, take your time. Let me see if I can fix this. Canvas. I don't know. Yeah, why they want us to be like so ghetto. So what do people do with all those towels? All right, let me change your grade. Do people find this quiz like there seem to be a lot more questions today? This material is like a lot more math, right?
Yeah. It just needed a lot of things. It's just a lot of different topics. Because when I was going through the textbook, there was just a bunch of derivations.
Yeah, we don't do the stuff with velocity as a function. We like that chapter is a little bit confusing because they have basically quiz 7 and quiz 6 both in one chapter, and we're not going to do quiz 7.
But you think just for the quiz preparation, maybe like just class examples of having
Yeah.
And just doing the stagnation points and on the pressure.
Yeah, that'll give you a pretty good prep.
Okay. Yeah, because I was looking at the textbook.
Patel, right? You're Patel. All right, hold on. Quiz 5, Patel. All right. What was your original grade? Okay, so we make it 15.5.
Okay.
That's the least I can do. Our previous grader has cancer,
Oh,
so she had to stop, and so we had to basically switch graders, and they're like, that's why stuff has changed a little bit in the semester. Yeah, she seems okay. She seems like it's getting taken out though. Is it, okay, now you have a question. Okay, and then you wanted to ask about the homework?
yeah.
Okay, do you guys both want to just talk about the homework? Have you done the homework too?
For this quiz?
Yeah.
I've started.